This is AS2 June 2014 and we're going to be looking at question 15b. So in order to answer this question we need to apply Gay-Lussac's law. So we're looking at 15b here. We're asked to calculate the number of moles of carbon monoxide. So we know that Gay-Lussac's law says that 1 mole of any gas occupies the same volume at a given temperature and pressure. So it's the number of moles of carbon monoxide produced, so we need to look at all the gases produced in our reaction. So you can see that's just our carbon dioxide and our carbon monoxide because our water is a liquid. So the only gases we produce here are 1 mole of carbon dioxide and 2 moles of carbon dioxide. So if we think about the total moles of gas here, total moles according to our balanced equation is 3, and out of those 2 out of 3 of them are carbon monoxide. So if each gas occupies the same volume, then we can work out the volume of carbon monoxide because we know the total volume of the gases produced. So if 2/3 of them are carbon monoxide, we can work out the volume of carbon monoxide as 2/3 times by my 9,000. And that's applying Gay-Lussac's law that your carbon dioxide and your carbon monoxide are occupying the same volume per mole. So 2/3 of 9,000 is 6,000 decimeters cubed. We then need to apply our molar gas volume equation. We're used to putting it in as volume is n times 24, but we've been told in the question that the molar gas volume is 30 decimeters cubed. So my equation is now volume equals n times 30 rather than n times 24. We rearrange that to get the number of moles. It's n equals volume over 30. The volume is 6,000, which we've just worked out. The molar gas volume is 30. So that gives us a number of moles of 200. Once we have worked out the number of moles of carbon monoxide, we can work out the number of moles of oxygen just by our ratio, our stoichiometric ratio. So you've got your propane plus 4 oxygens giving you 1 mole of carbon dioxide, 2 moles of carbon monoxide and 4 moles of water. So we've just worked out that we have 200 moles of carbon monoxide. So if I want to work out my number of moles of oxygen, I just use my balancing number ratio, which in this case is 2 moles of carbon monoxide to 4 moles of oxygen. I'll just write it so it is underneath the correct part of the equation. So essentially it's a ratio of 1 to 2, but we're working this way. So we need to times our number of moles of carbon monoxide by 2. And that gives us 400 moles of oxygen. We're then asked to calculate the mass of propane burned, and in order to do that we need to first work out the number of moles of propane. The only way we know to work out mass is by doing n times RFM. So we've got C3H8 plus 4O2. We'll just write out that part of the equation, that's all we really need. We've got 400 moles of oxygen. Look at our ratio, it's 4 oxygen to 1 propane. So we have burned 100 moles of propane. So if we've got 100 moles of propane, we then put that into our equation, mass equals n times RFM. The number of moles is 100. The RFM of propane works out as 44. So that gives us a mass of 4,400 grams, but the question specifically asks for it in kilograms. So we need to divide by 1,000, which gives us 4.4 kilograms. Then the last part of the question asks us to work out the number of molecules of propane burned. How we get the number of molecules or number of any form of particles is we take the number of moles and we times it by Avogadro's number, Na. We worked out in the previous part that we have 100 moles of propane. Avogadro's number is 6.02 times 10 to the 23. So that gives us a number of molecules of 6.02 times 10 to the 25.